Assalamualaikum. In today's episode, we focus on computing the dioptic power of a contact lens required to have sharp image of a close object by an artificial eye lens that had been designed to focus on distant objects. To better understand this, just stick around, watch, and learn. The question is, in one form of cataract surgery, the person's natural lens, which has become cloudy, is replaced by an artificial lens. The refracting properties of the replacement lens can be chosen so that the person's eye focuses on distant objects. But there is no accommodation, and glasses or contact lenses are needed for close vision. What is the power in diopters of the corrective contact lenses that will enable a person who has had such surgery to focus on the page of a book at a distance of 24.0 centimeters? In this problem, we consider the distance of the page of a book from the eye lens as the object distance DO equal to 24.0 centimeters. Since the artificial eye lens focuses only on distant objects and there is no accommodation or the ability of a natural eye lens to vary its focal length from a relaxed to a dilated mode, glasses or contact lenses are needed for close vision. In which case, we consider the near point to be at infinity. Without wearing glasses or contact lenses, a person with farsighted eye cannot see a sharp image of an object located less than the near point. So, our goal is to find the required focal length, small letter f, of a contact lens or glasses that would enable the artificial hyperopic eye lens to focus an object at an object distance um, d sub O, right? So our target variable is the power of the lens required in diopters. Recalling our past lesson on vision defects, we said that for any natural farsighted or hyperopic eye, the image of a near or close object is formed not on the plane of the retina, but behind the retina. So the vision is blurred. And this happens because the eyeball is either too short or that the cornea is not curved enough. This can be corrected by wearing a converging lens, which creates a virtual image of a close object at the near point of a farsighted eye. All right. So the virtual image that is formed by the converging lens uh, becomes the virtual object of the eye lens. All right. So the eye lens now forms the sharp real image on the plane of the retina. So moving on to our computation for the required focal length of the contact lens, okay, we apply the thin lens equation, which says that the reciprocal of the focal length, that is 1 over f, is equal to the sum of the reciprocals of the object distance and the image distance. So substituting the given data, we have 1 over f, or the reciprocal of the focal length required, is just equal to 1 over 24.0 centimeters plus 1 over infinity, right? So the magnitude of the focal length, small letter f, therefore, is equal to positive 0.240 meters in three significant figures, right? Um, 1 over infinity, as you may all know, is equal to 0. So that is how we got the value for the focal length equal to positive 0.240 meters. The positive sign is emphasized here to mean that the lens that is required is a converging lens, right? By convention, a converging lens, okay, has a focal length that is considered positive. So finally, we can now proceed in computing the power of the lens, right? Which is simply equal to the reciprocal of the focal length expressed in meters. So that is, the power of the lens is just equal to 1 over positive 0.240 meters, which is equal to 4.17 diopters in three significant figures. And that concludes our video lesson for this topic. Till the next episode, mabuhay, Masya Allah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.